Welcome to part 2 of module 202B. Now that we've looked at what a resistive inductive circuit looks like, we're going to look at a resistive capacitive circuit and kind of look at some of the differences. To be honest, most of the calculations and everything else that we're going to need for an RC circuit are the same ones that we already use with our RL circuit. So let's get started. When I look at this circuit and consider the voltages within it, I want to think about the phasors that go along with each component. With my resistor, we already know that a resistance is in phase. Therefore, the voltage of my resistor should be on the reference line with the ampacities. When it comes to my capacitor is known as a leading component, which means that current leads voltage. Therefore, when I think about how on my phasor diagrams, everything rotates around and counterclockwise, I want to see the current passing by the reference line before the voltage. That means the voltage has to be behind it. Because of this, we show our capacitors at 270 degrees or negative 90 degrees. As a result, when I have a series RC circuit that has both resistance and capacitance, my total voltage, even though I know it's going to be 120 volts, its phase angle is going to be somewhere between 0 and 270 degrees, or between 0 and negative 90. When it comes to looking at the impedance diagrams for an RC circuit, they are the same thing as an RL circuit with one minor detail. They go down, they don't go up. That's because my XC component goes in the opposite direction to my XL component. Therefore, if my XL in my series circuit goes up because it's lagging, my XC goes down because it's leading. And I should represent that in my diagrams. I still have my horizontal be my R, my vertical be my XC, and I can use Pythagorean's theorem to figure out what my Z is going to be. Once I have my Z, I can therefore find my current, which is my constant inside the series circuit, and then I can use the current with each one of those components inside my impedance triangle to figure out the individual voltage values of each individual component. And once again, when I look at my impedance triangle, my power triangle, and my phasor diagrams, they should all represent each other. They are all the same angle and all the same proportions between all the sides. The one thing that's also going to be constant is my power factor angle or my power factor. It will be the same for each one of these. When it comes to solving for power inside an RC circuit, it is the same thing that we do with an RL circuit. We're going to use all the exact same formulas. The thing that we need to remember is that anytime I want to find something on any particular line, I have to find all the values of that line. For example, to solve for true power or P, since my resistance is on that line, I must use my resistance. So I squared times R, for example. For my reactive power, I have to use my capacitive reactance, I squared times XC. For my apparent power, I want to use my total voltage and my total current, or my total voltage and my total impedance in order to solve for my apparent power. Make sure you're using the right values. That is the most common mistake people make, is they confuse which line to use. Everything on the horizontal, use just horizontal numbers. Anything on the vertical, just use vertical numbers. Anything on the hypotenuse, only use the hypotenuse numbers. As I mentioned before, in order to solve an RC circuit, we use a lot of the same things that we already used to solve an RL circuit. However, if you need to go through the information, now is a great time to do that. Watch the rest of this video until you get a good handle on what we're doing in order to solve these circuits. Once you're comfortable with that information, go ahead and look at the circuit that is on the screen and see if you can solve it. Of course, the very first step, since I've only given you capacitance, is to solve for your capacitive reactance. Pause the video here and continue it when you're ready. All right, so we have our capacitance. The next thing we need to find is our capacitive reactance. I'm going to use my formula. Xc is equal to 1 over 2 pi Fc times 10 to negative 6. The 10 to negative 6 automatically converts it from farads to microfarads for me. So since my capacitance is in microfarads, it's going to give me my ohms in the right value. So with this formula, with the 10 to negative 6, I can just put in the 26 instead of 0.000026. Just a small adjustment to my formula helps me out with my calculations. As long as you understand why it works, go ahead and use it. Now that I have my total XC value, I can work on my impedance triangles. So with my impedance triangles, I have my resistance and I have my capacitive reactance. Using Pythagorean's theorem, I can now calculate what my total Z is going to be. Remember, my Z value is what I need in order to find out what my total ampacity is going to be. I need my total impedance with my total voltage to find total ampacity. The other thing I can find out with this impedance triangle is what my power factor and my operating angle are going to be. So, adjacent divided by hypotenuse, which would be R over Z. I can find that 0.843 is my power factor, and it's a negative 32.523 degrees. So once again, we are between the 0 and 270, or between the 0 and negative 90. So it's a negative 32 degree operating angle. The next step is to find my current. Remember that current is the thing that we're going to use in all the formulas from here on in. So I take my 120 volts, divided by my total impedance of 189.759 ohms to get a total ampacity for my circuit of 0.632 amps. And this is also the ampacity for my resistor and my capacitor at the same time. Since I have my ampacities, I can use my Ohm's law formula in order to figure out what my voltages are for both my resistor and my capacitor. And I can verify these voltages with my meter on the circuit as well. So I times R gives me a voltage value of 101.12 volts, and that's at 0 degrees since it's resistive. And I also have a voltage of XC of 64.478 volts, and that is at negative 90 degrees since it's capacitive. It's good to know the voltages as well as the phase angles for those voltages. The next thing I want to find is what is my power value of everything. Once again, my power formulas that we used before being I squared R and I squared XC will go a long way to help me out for all these things. So S can be my current multiplied by my total voltage. Since my total voltage was given to us, that's good value to use. And since my current is my constant, that's the other good value to use. So I can use the E times I formula. I should have a VA of 75.886 VA. My power is going to be I squared times R. Once again, since I is my constant, I want to use that as many times as I can. And that should give me 63.985 watts. And my Q being I squared times my XC to give me a total of 40.799 var. Keeping in mind that all these things should equate to each other when we look at them in the triangles. So as I apply things to the triangles, when I figure out the phase angle of my power triangle compared to the phase angle of my impedance triangle, they should be the exact same angles. So use Pythagorean's theorem to make sure everything checks out and you haven't made a mistake. If your numbers are not jiving at this point, you have to go through and find out what went wrong. If you made it through that circuit without getting lost, then it's time to give you another one. If you were confused about anything that we did, make sure you are reviewing the video as many times as you want. And if you are still confused, feel free to contact me about any of this information. In the meantime, if you're all caught up with where we are, let's go ahead and solve this one. Pause the video and then resume when you're ready and you've solved this circuit. To start solving this circuit, I had to find out what my capacitive reactance is going to be. Therefore, I'm going to take my formula, XC is equal to 1 over 2 pi FC times 10 to the negative 6, so I don't have to convert it from microfarads, and I get a total capacitive reactance of 20.404. Now I have enough information to build my impedance triangle. With my resistance being 110 ohms, my capacitive reactance being 20.404 ohms, my total impedance for my circuit is 111.876 ohms. This gives me enough information to find out what my total ampacity is going to be. However, before I do that, I can still find out what my phase angle as well as my power factor. That's still going to be the same. We're adjacent over hypotenuse, or R over Z. And I should come out with a power factor of 0.983 and an angle of negative 10.507. So now I will use Ohm's law in order to find my current. Now, since I have my total impedance, my Z value, I divide my voltage by my Z, in order to find my current of 1.073 amps. This is the number I'm going to use in the rest of my formulas, so it's important that we have this one. I can use that ampacity in order to find out what the voltage across not only my resistor, but across my capacitor is going to be as well. So I'm going to use my formula I times XC in order to get V, and that is going to be 21.886 volts, and that should be the voltage across my capacitor. My VR is going to be I times R, which is going to be 117.987 volts across my resistor. These are both measurable, so we should be able to double check with our circuit to make sure that this is correct. Lastly, I'm going to figure out my power. Now my power triangle and my impedance triangle should reflect each other. In order to figure out my power, once again, my total apparent power, I want to use all my other total values. So I can use my total voltage and my current. I can use my total voltage and my total impedance, or I can use my total impedance and my current. Either way, I must be done with the total values. The most reliable ones to use are my voltage, which is given to me, and my current, which I'm using as my reference for everything in the circuit. So S is equal to E times I gives me a total apparent power of 128.714 VA. To figure out my power, I use my current again, I squared times R in order to get a wattage of 126.556 watts. And for my reactive power, it's I squared times XC, which gives me a total XC of 23.475 VARs. When I put all these numbers into the triangle, I should still have the same power factor as well as a power factor angle of that triangle. Make sure you're using your trigonometry and Pythagoras in order to double check your numbers. It's going to help you find any mistakes that you make. So that's it. That's what this circuit should look like. If you have any questions, go through the video again and don't be afraid to contact me. I'm more than happy to help. You've now completed Module 202B, so you can return to Blackboard and work on the worksheet that I have there for you. Make sure you do the knowledge check, and then you can continue on to Module 202C.